Hello and welcome to this presentation on visual odometry. Before we can talk about visual odometry, we have to clarify what actually is odometry. And in general, odometry is the process of using sensor data from a robot or vehicle to estimate its position over time. And generally speaking, odometry can be seen as a simplification of SLAM, which is simultaneous localization and mapping. And odometry is way less computationally expensive, and so it has its own use cases, but it suffers from some other problems which we will get into in the future. And so when would you use visual odometry and odometry in general? And this is basically always when you have no global positioning system available, so GPS, or if you have a really low latency requirement, because odometry is most useful in very low time steps and not really good if you have a really long sequence you want to estimate position of. Then it's usually used in driver assistant tasks or in autonomy, for example, in the Mars exploration missions, because you don't really have a global positioning system on the Mars, so you have to use other means of localization. And you usually don't have the resources to do a full SLAM algorithm at runtime on the Mars. And some virtual reality devices use visual odometry and SLAM-based systems to localize themselves in the environment. So the visual odometry can be used for tracking these devices. Probably the most common form of odometry is wheel-based odometry. In this case, you put wheel encoders or rotary encoders on each wheel of your vehicle, and based on the rotation information the wheel encoders provide you and the intrinsic parameters of the vehicle, so the distance between the wheels and the radius of the wheels, you can then integrate the position of the robot over time. However, as each position is based upon the previous position, the errors you encounter with this problem accumulate, so it gets worse and worse over time. And for example, on the Mars exploration mission Opportunity, on a 19-meter uphill section, the wheel odometry had an error of about 1.6 meters, which is equivalent to about 10%. This is due to the wheels slipping, so the encoders think the robot has actually moved, but in reality the wheels just moved in place, so the position error is determined in the wrong way. And together with visual odometry, this error was able to be reduced to about 1%. So now to visual odometry. As the name suggests, visual odometry makes use of visual sensors like cameras or LiDAR sensors to estimate the position of the platform over time. But visual odometry also comes with its own problems. For example, it struggles with HDR environments, so high dynamic range environments, where the brightness of the scene changes rapidly. This is especially a problem with camera-based odometry, as the camera exposure is usually adjusted to a specific brightness of a scene, and if the brightness of a scene changes abruptly, for example, as in this clip when you enter a home or when the sun suddenly comes around a corner, the image becomes over or underexposed, and so it's very hard to detect any features in the environment, and so the tracking is very hard or even impossible. So one point which is important for visual odometry is that you require a feature-rich environment to estimate the position in. And of course, similar to wheel odometry and other forms of odometry, you have drift which accumulates over time, and depending on how good your tracking environment is, this might be good or not so good. And another problem with visual odometry is the rigid world constraint. So you assume that the world remains a constant and doesn't move, because in the worst case, you could imagine that the platform actually stays stationary, but the world moves around the platform and the camera. And so the algorithm would be unable to determine if the platform is actually moving through the environment or in reality the environment is actually moving around of the platform. And in a less extreme case, maybe some car is driving in front of the camera, and while the car is obscuring the camera, the visual odometry algorithms might determine that the environment is moving to the left or to the right, but in actuality the platform is staying put and just some parts of the image are moving. And if parts of the image are moving in different directions, the algorithm might become confused what actually is the environment and which parts should be used for determining the position through the environment. And second problem with odometry would be that it's computationally expensive. You have to process very high resolution images to detect features and detect motion from these features, which might be problematic in embedded environments which don't have a lot of computational resources. So there are many different possible algorithms for visual odometry, and we want to look mainly on camera-based odometry. And there the main differentiation factor is probably the number of cameras you have. In the most basic case, you have a single camera, so monocular odometry. And of course, the advantage of this system is that it's pretty simple, and because you only have a single camera. But it also has a problem because as you have only one camera, you cannot estimate the depth or the scale of the scene. Of course, we humans could estimate the scale of the scene based on known scales. For example, if we see a human in the image, we know approximately that this human will be about 1.8 meters tall. And from this, we can extrapolate the rest of the scene's scale. But we cannot algorithmically determine the scale of the environment, and so we can only calculate a relative path which the platform took through the scene. And even this algorithm has some problems because we get like a set of 2D feature points from these algorithms, and we have to somehow begin to estimate the 3D position of features over time, and this is a process known bundle adjustment. So we match feature points between multiple frames, and then we try to find viewpoints from which we could extrapolate the base scene structure and geometry. And in comparison, stereo odometry or multi-camera odometry is a bit more complex of a setup because we have to determine the distance between of these cameras and have to calibrate them. But this allows us to get a more accurate depth perception. However, this is also based on the baseline distance between these two cameras. And if the feature point is far more away from these cameras, then the cameras are separated themselves. This case converges towards the monocular case, and it becomes basically impossible to determine the depth of the feature point because the changes from the left to right camera image become basically negligible, so subpixel. So yeah, we cannot estimate the depth from this anymore. As a very rough first overview, we can separate the visual odometry algorithm into multiple steps. So first of all, we have to calibrate the camera images because with a distorted image, we cannot do any accurate motion estimation. Then, of course, we have to capture images from the cameras. In case of the stereo visual odometry, we have to compute a disparity map. So extract the depth map from the stereo images. Then detect features in these images and match these features to previous features we detected in the previous frames. And from these changes in the feature positions, we can estimate a motion of the observer. So as the first step, the camera calibration. This is mainly done using some calibration patterns that have a known grid structure, and we can capture a few images of these grid structures in front of the camera. And as we know how this structure should look, we can estimate distortion parameters of the camera and undistort the image. In case of a stereo setup, the next step would be the computation of the depth map using a semi-global block matching algorithm. And this algorithm basically goes in horizontal lines from the left and right image. And we take a look at a small window of the left image and try to find the same pattern of pixels in the left image. This is done by using a minimization algorithm, which minimizes the similarity of the block between these two images. And we have this maximum disparity parameter D, and based on this, the right image is scanned for this feature from the left image. And then we save this disparity for each pixel, and this results in a depth map. And based on this depth map, we can then reconstruct the scene depth using the known parameters like the distance between the two cameras and this disparity parameter. The next step would be the feature detection. There are multiple different algorithms which can be used for this, and probably the most common one is the Harris corner detection algorithm, and there are many more algorithms which do similar things like FAST, IF-SURF, ORB, or in recent years neural network-based approaches have become very successful. An example for this would be SuperPoint. And part of the feature detection is also the building of a feature descriptor. A feature descriptor is more or less a digital fingerprint of the feature. And ideally, this feature description is independent of image transformations. So if we have the same feature in two transformed images, ideally the feature descriptor would be the same for both feature points. And then we could use this feature descriptor to match both features in the two images. One common problem in this feature detection step is the clustering of features in a single area of the image. And this can become problematic if this area moves outside of the next image which is captured. So most of the feature points are lost and the tracking algorithm cannot work properly anymore. And to prevent this, a bucketing algorithm is usually employed. And this basically separates the image into a lot smaller images and detects the X best features in each of these grid cells. And so we have a more even spread of feature points over the whole image. Next up, I would like to take a short look at the Harris corner detection algorithm. It was developed by Chris Harris and Mike Steffens in 1988. And it tries to find a heuristic for finding corners in an arbitrary image. And it is based on that a corner is usually in a place where the brightness derivatives are large in all of the directions based from this center pixel. And it uses some complicated math I don't want to get too much into, and it results in two values, lambda 1 and lambda 2. And generally speaking, if these two lambda values are large, then the pixel can be is probably a corner. And yes, then based on some threshold, we can detect corners from an image using this algorithm. So once we have detected features in the last image and in the current image, we somehow have to match these features. So corresponding features are matched between both of these frames. And probably the most straightforward approach would be a brute force, but obviously this is not the most efficient method. And as usually two consecutive images have not moved that much, the feature points will also not have moved that much, so a nearest neighbor search can be really good. And for that in OpenCV you can use the Flan matcher. This is a fast library for approximate nearest neighbor matcher, which is implemented in this library. And a different approach would be using neural networks, and SuperCLUE is a neural network specifically trained to match feature descriptors using a deep neural network. And in this animation below, you can see the SuperCLUE network at work trying to match features from two images. And on the left, you can see the base image. On the right, you can see the same scene with a transformed view. And you can see these colored lines, which represent matches the neural network thinks it has found. And the red color represents a high confidence, and then as it gets the lines colored towards blue, the confidence of the neural network decreases, and you can see that in the beginning it's very confident, but as the transformation of the scene continues to increase, the neural network becomes less and less confident that it has found correct matches. Even now we have detected the same features from two consecutive images, we still cannot use these features for predicting the movement of the platform directly. This is because maybe we have detected a feature on a car and we have perfectly matched this same feature from between the two images. However, as the car might have been moving during the capture of these two images, we would falsify our motion estimate. And for this, we need an outlier detection, or a different approach would be an inlier detection. So we are assuming that the scene is rigid. So this means that the same two features in the original image would have to be the same distance from each other than in the next image. And this is also a reformattation of the rigid scene constraint from before. And this problem can be expressed as a matrix, and so we set a 1 for each feature point which has the same distance in both of the point clouds, and a 0 otherwise, and then this can be interpreted as a graph. And basically reforming this problem yields the max-clicker problem. And this is of course MP hard to solve, but we basically want to find the largest subset of features which remain a constant distance from each other in both of the captured images. And we can use some approximation algorithms like RANSAC to make this probabilistically a lot cheaper, but of course it does not guarantee an optimal solution, but in the normal case this works pretty well. And once we have matched and detected all of the inliers from two images, we can now estimate the motion between the two consecutive frames. And this is done by finding a transformation matrix T, which includes a rotation and a transformation of the camera. And we calculate this matrix by minimizing the reprojection error, which is defined by this formula you see up here. And this can be achieved by the Levenberg-Marquardt linear least squares minimization algorithm. And this basically just takes as an input our two consecutive feature sets and the variables for the transformation, and it spits out the values which best minimize the error from the reprojection. And this basically gives us a matrix which describes the transformations in the last frame. And if we combine all of these transformations together from all of the frames, we get a path of the motion. So what we've looked at so far is basically feature-based visual odometry for monocular or stereo cameras. But there are also direct or semi-direct approaches which do not estimate the motion based on singular features, but a more direct movement of the scene. And Another approach which is often used is data fusion. So we combine the visual information with other sensor data like IMU data, so inertial measurement unit data, which is also present, for example, in your phone. And then it's called visual inertial odometry. And of course, you can also use wheel encoders, and this could kickstart the nearest neighbor matching because we can reproject the 3D features from the next frame based on the data from the wheel encoders. And of course, this won't be 100% accurate, but it can improve the original estimation of motion and thereby simplify and improve the results of the visual odometry. In the following, you can see some graphics of the use of visual odometry and odometry in general on the Mars exploration mission Opportunity. And in the first graphic, you can see that visual odometry was used only in parts of the navigation on the Mars. And this is mainly because of limited resources and the computationally expense of visual odometry. And so in cases where low wheel slippage was expected, mostly wheel-based odometry was used, and only when driving uphill, the more complex visual odometry was used to improve the accuracy of localization. And you could see a plot of the wheel odometry error in comparison to the visual odometry error, and of course the visual odometry error is much lower. Of course, it's always hard to get a really correct ground truth on the Mars, so just take these data with a bit of grain of salt. And here's a graphic of the path predicted by the wheel odometry in comparison to the visual odometry, and you can see that there's a quite extensive difference between the two. And just to visualize that these methods are not perfect, and optimally you would use something like SLAM and post-graph correction and loop closure to improve these results. So this was it with my presentation on visual odometry. In case you have any questions, feel free to ask them. And apart from this, have a great day.